dans le chat. Donc, si vous voulez vous joindre à nous plus tard, donc vous allez pouvoir prenez ce lien-là avant qu'on referme la conférence. Juste vous parler, j'espère que ça a bien fonctionné la dernière fois. Je pense que oui. L'envoi du certificat va se faire de façon automatique demain, donc une journée plus tard exactement, donc demain soir. Si vous ne le recevez pas, donc vous pouvez nous envoyer un courriel à notre adresse courriel que vous pouvez trouver sur notre site Internet. Mais je pense que ça va très, très bien. Donc, vous allez recevoir votre certificat de la journée. Si vous ne le recevez pas, peut-être aller voir dans vos indésirables naturellement. Notre prochaine conférence, on va parler dans une nouvelle maison de Radio-Canada. On va avoir la chance d'avoir Valérie Chartrand de chez NCK qui va nous parler de ce projet-là. Vous pouvez dès maintenant vous inscrire à partir de notre site Internet. Il y a un lien pour s'inscrire à la même conférence, donc GoToWebinar. Donc, ce soir, pour notre programme principal, donc, M. Perry Adebar est avec nous ce soir. Donc, je vais vous le présenter. Juste 2 petites secondes. Je vais. Pardon, c'est pas une technique. Donc, Professor Perry Adebar is chair of the Standing Committee of Earthquake Design, responsible for Clause 4.1.8 in the National Building Code of Canada, and is chair of the Technical Subcommittee of CSA A23.3, responsible for Clause 21. So I will let Mr. Perry Adebar share his screen right now. I've been trying to have Mr. Adebar with us for 2 years now. We are now fortunate to have him with us tonight. Please welcome Mr. Adebar. Mr. Adebar.
Thank you, Steve. So how do I share my screen?
Just a minute, and I'll give you the. Okay, it's yours.
Okay. Do you see my screen?
Yes, we see your screen, Mr. Adebar.
The title page, yeah?
Yes.
Excellent. Okay. Well, thank you very much, Steve, for inviting me to talk to you on a very interesting subject, the analysis and design of concrete shear wall buildings below the plastic hinge. And this is, of course, a new requirement in CSA A23.3. We have some new clauses in the 2014 edition. And there are a number of other clauses in NBC, for example, which relate to this. So I was told to spend about 55 minutes presenting and then leave a bit of time for questions. So that's my plan. I should be done in about 55 minutes. So to start off with, the simple picture of what we're dealing with really is the idea that you have this tower wall that comes down a building, and then below grade, it's tied in with a number of diaphragms into the foundation walls. And people have noticed, of course, when they do an analysis of the building, they notice that you get very large shear forces. So I'm looking at the shear force in the cantilever wall direction over the height of the building. And here is the base shear coming here. And of course, we get a very large increase in shear force below the base. And the question is, do we have to design for that shear force? Sometimes it's 2 or 3 times the base shear. And so the question has been asked, do we have to design for that? Can we assume that a little bit of cracking and that shear force will go away? And that's really the issue we're talking about today, is how to design for these very large shear forces that occur when you do an analysis of a shear wall coming down to the below grade diaphragms. And I'm going to start by quickly reviewing some code clauses that are relevant. I hope that my pointer works. and that people can see what I'm talking about. So the first section, let's just look at some code clauses, and then we can talk about how to do the problem. So the very first one, I don't know what version of the Quebec Building Code this is, but this is in the 2015 National Building Code of Canada, which is certainly the current building code in most provinces. I assume it's the one in Quebec. The clause 418.16 under foundation provisions said that you have to account for foundation movements. You have to account for foundation movements to consider what is happening both to the SFRS and the structural framing elements not considered part of the SFRS. And of course, foundation movements mostly affect the gravity frame or the structure that's not the SFRS. Any movement in the foundation will actually reduce demands on the SFRS, the shear walls, but will increase the demand on the gravity frame. And NBC says you have to account for that. Then if we go to CSA A23.3, 2014, there are a few clauses that are important for our discussion today. So we go to 2110 foundations. There's two methods, and we'll just look at the one method, which is 2110.2, which is foundations restrained against rotation. You can do a simplified method. So let's just talk about that, because the problem we're dealing with, the foundation is restrained. It's 4, 5, 6 levels below grade. It's not free to move. And so if we look at clause 2110.2, that first of all, it says you can do this if the structure is shown to have sufficient stiffness and strength to restrain movements. And a structure below grade like that is certainly going to have that stiffness and strength. And then it gives as an example, it includes foundations supporting shear walls that are connected by multiple diaphragms to separate foundations. So this is exactly the problem we're dealing with. And so 2110.2 is an important clause that we need to consider. Okay, and when we look at 2110.2, the first thing it tells us is we need to design for the nominal overturning capacity of the SFRS. And I'll be calling that M sub N in our presentation. So number one, we've got a capacity protect the foundation, and the level of protection is the nominal strength. The next thing it says is in 2110.2.3, it says if RD is greater than or equal to 2, so that's moderately ductile or ductile systems, then you have to also satisfy 21.5.224 and 21.5.229. Okay, and these are the clauses that we're really going to focus in on. And I think in Montreal, you probably design moderately ductile high-rise buildings. And of course, in Vancouver, on the West Coast, we design ductile. So both Montreal and Vancouver, you must satisfy these requirements. Okay, and if we just look at 21.5.224, just quickly, you know, one of the things you have to do is make sure you design for the right factored flexural resistance. So the right factored bending moment, sorry, that's really, and so one of the things you have to do is scale that based on your overstrength, okay? The second thing you have to do is this analysis according to 21.5.229. Okay, so you're required to do that, and that's really the focus of the conversation. When Steve invited me to talk, he said, come talk to us about 21.5.229. That's really the issue, and I will talk about that. And then finally, there's this requirement that you provide additional 20% reinforcement below the plastic hinge. And the reason for that is we don't want yielding to propagate down into that zone. If we get yielding below that grade level, where we get these stiff diaphragms, we will have serious problems. So to prevent that, we actually have to add reinforcing steel. So that's an overview of all the design clauses really that kick in. And then we're really left with the focus of my conversation today is 215229, designed for shear below the plastic hinge. That's the topic of today, really. So this is like an introduction. Okay, and what this says is that if your shear wall is connected to stiff supporting structure by multiple floor diaphragms below the plastic hinge, then your shear force, your factored shear force and bending moment must be determined using analysis that considers lower bound or upper bound effective stiffness as appropriate to determine a safe estimate of shear force. So this lays out that you have to do a detailed analysis. And because we really don't know the stiffness of the complicated system down there, you can't just assume one value and then do the analysis and be done. This says you have to look at it carefully. The results are very dependent on what stiffness you use, and therefore you need to consider a range of stiffness. And indeed, the conversation today will be a lot about the stiffness of diaphragms. And then it points to the commentary, and there's much more information in the commentary, and I'll talk about that. Okay, so now let's start. So that's the code clauses. That's the background that we're satisfying all those clauses, all of them. And now let's talk about, how do we actually do this? How do we accomplish this? And of course, it's a multi-step. Okay, and the first step in the design of a building would be a global analysis. Okay, like a linear dynamic analysis. I think we all do that. Some people like to use non-linear, but very few. And the main purpose here is to determine the seismic forces and the deformation demands on the system and components, really from what's going on above the base. So we're going to model the concrete tower walls in this zone. We're going to account for effective stiffness, but below this zone, we're actually going to model it as uncracked. Okay, so let's look at the assumptions. Number one, rigid soil. We're not going to model soil flexibility at this stage. Okay, so we still have to come back and think about that, because the National Building Code of Canada says you have to account for soil flexibility. Okay, and we're going to, but we're not going to do it here. We're going to do it later. Okay, then we're going to do the uncracked concrete below the base. So everything below the base, everything down here, we're going to say is uncracked. Okay, but we are going to model it. We are going to model the tower wall going down. Okay, and we're going to account for the flexibility. So what does that mean? That means, for example, that we are going to get some drift here, right? There is going to be movement there. It's not going to be fixed. Okay, there is flexibility, but we're going to use an upper bound stiffness down below. Okay, and what's the purpose of this? Purpose number one is to make a safe estimate of the force demands in the wall above. Okay, the stiffer the structure, the higher the forces. Okay, but we're also going to use it to estimate the displacement of the building. Okay, but mostly due to what's happening above the base. Okay, there is some contribution from below the base, but we know right off the start that this is not the complete estimate of displacements. The displacements will be larger than what this analysis will tell us. Okay, we're doing a two-step analysis. Okay, in one case, we're getting a safe estimate of the forces. And then in a second step, we're going to look at what's really happening below the grade and look at the additional displacements. Okay, and then this is an example, as we saw a minute ago, this is an example of the kind of results we get from the global analysis. Okay, and this happens to be the one out of the handbook, and I'll talk more about that example. But again, base shear is here, great big giant shears down here, okay, because of those stiff diaphragms. Okay, and we're going to get, of course, bending moments, right? The bending moment, and the key here, of course, is that the reason the shear is so large is, of course, because the bending moment is reversing. Okay, we're getting this huge reduction in bending moment, and of course, that is directly linked to those large shear forces. Now, what's next? We've done our global analysis. We have our forces above grade. Okay, we need to do some design before we can move forward and do the refined analysis. For example, we're going to have to design the coupling beams over the full height of the structure. Okay, and then once we have our coupling beams designed, then we can determine the increase in axial force in the coupled wall piers and the actual strength of the coupling beams. Okay, so we have to design the coupling beams because we need to know what is the actual strength of the coupling beams in order to complete the design. And of course, then we can design the vertical reinforcement in the wall piers, because now we know what the coupling beam strengths are. Okay, and now we can determine the nominal and probable resistances of the wall system. Okay, only now can we do that. And now we're ready to start the analysis of the base. The thing we also could do is determine the wall deflections. Okay, now that we know the nominal resistance, we could come down here and calculate with a refined effective stiffness if we wanted to. Okay, it's only after we actually know the strength that we can then make accurate estimates of the stiffness. And if we want to, we can go back at this point and say, let's take the global model and let's refine the stiffness and make a better estimate of the displacements. Okay, but it could be a lot of work, and you might just say, you know what, I'm happy with a lower effective stiffness up above and larger displacements. Okay, that's often what you would do. Okay, and now we're ready. Only at this point are we ready to say, let's do the refined analysis below the base. So important to note, this analysis comes after considerable design work. Okay, and what does this look like? Okay, so this refined analysis, okay, so it's refined analysis and it's only the structure below the plastic hinge. Okay, so it's all the structure that we sort of modeled very simple. We just said it was uncracked. We ignored the soil. Now we're going to look and see what's really going on. Okay, what's really happening in the soil? What's really happening in the diaphragms? How cracked are the diaphragms? How cracked is the shear wall down there? Okay, and all of that happens here in this analysis. Okay, assumptions. We're going to account for soil flexibility. Okay, in this analysis, we're going to do what NBC requires and is account for soil flexibility. And we're going to consider a range of stiffness values for the elements below the grade, exactly like that CSA clause says we have to do. Okay, what's the purpose of this analysis? It's to get the design forces in the elements below the plastic hinge. Okay, this is where we find out the forces down there, including the tower wall, you know, what's happening in the actual tower wall, what's happening in this zone, okay, as well as what's happening in the diaphragms and what's happening in the foundation walls, and really important, what's happening down here in the footing. And we can now, only now can we design the footing after we do this. Okay, so that's the first thing, is this idea of a global analysis with one set of assumptions, and then we've got a refined analysis. The other really important point is that in Canada, we permit you to apply a static bending moment. Okay, this can be a static analysis. And in the US, when they do this, they typically include this in their time history analysis. Okay, but we've come up with a clever way that allows you to do this using static analysis. Okay, and the moment you're applying here, well, it might be MN if you're looking at the strength of the foundation. Remember, that's what the code said. Or it might be MP if we're worried about shear strength of the wall, because that's what we have to design for. Okay, so we're now into the analysis below the base, okay, with the applied moment being the actual strength of the shear walls. Now, why do we have to use different stiffnesses? I mean, that's an important question. Why can't we just come up with a reasonable set of stiffnesses and then do it? And the answer is this, that there's two load paths for the bending moment, okay? The bending moment's coming down here, okay? And it could just go straight down, right down to the footing. And that's this route, okay? So one route is just straight down the wall to the footing. Okay, and then the footing can take out that moment. But there's a second route, and that second route is where the bending moment goes out, oops, sorry about that, where the bending moment goes out to these forces here. Okay, the diaphragm forces. So the moment can all go out there, right? By having two force couple in those diaphragms, you take the moment out into the foundation walls. And that's the reason why the stiffness is so important, because it's an indeterminate system, okay? And, you know, if it comes straight down, then the moment in the wall is high and the moment in the footing is high, and the shear in the wall is low. But if it goes out into the diaphragms, then the moment in the wall is low, the moment in the footing is low, but the shear in the diaphragm can become very large, okay? And of course, that's one of the things we're worried about is that we do, in fact, a diagonal crack in the wall. Okay, so the commentary to clause 21529, okay, the clause we're talking about, the commentary says that you have to do a number of load cases, okay? And so we've got case, and I've called it 1, 2A, 2B, and 3. So it's really 4 cases, except you know what, 2A and 2B are so similar, that's why I called it 2A and 2B, because there's only one small difference. Okay, case number 1 is where we get the maximum bending moments in the tower wall, the design forces for the foundation. In other words, case 1 is where the moment is going, as much moment as possible, goes straight down. Okay, case 2 is where we're getting the forces in the diaphragms, the podium structure, and other walls. Okay, and the shear force in the tower walls. Okay, and 2B, we make a small adjustment to get the maximum shear force. Okay, because we're trying to pick up, by the way, we're trying to pick up what you can do with a dynamic analysis, with a time step analysis. And in a time step analysis, that shear force is going back and forth. It goes to a maximum value, and then it comes back down through 0. Okay, and we want to do all that with a static analysis, and that's why we have to do these multiple cases. Okay, because in that cyclic behavior, there'll be a time when the shear is maximum, and there'll be a time when the base shear I'm talking about. There'll be a time when the base shear is maximum, and there'll be times when the base shear is 0. And it turns out that influences what's happening below the base. And then finally, case 3 is where we're going to get the interstory drift ratio of the tower walls at the top of the structure. So this is where we get the additional drift, and that we're going to add to what we got in the global analysis. Okay, we're going to get that out of case 3. And this just shows that same thing again. I'm probably repeating myself too much. Case 1, right, moment is going straight down to the footing. That's what we're interested in. In case 2, we're interested in how much of it is going to end up over here. Okay, so just shown very simply. Okay, and again, case 1 is for the vertical reinforcement design in the tower, as well as the footing design. And case 2 is for that very critical shear design. Okay, you know, right in this zone here, where we're could get a shear failure, and we're worried about that. Okay, just looking at it in more detail. Okay, and we can spend an hour or 2 hours just on this subject, but we're not going to. This lays out a bit more what you're going to do, right? So again, our cases: case 1, case 2A, 2B, and 3. Okay, and 1, as we said, we're after the foundation design and the tower wall flexural design, and that's why it's MN. Okay, in the case of the case 2, we're after diaphragm forces, diaphragm shear forces. We're interested in the shear force in the tower wall, and it's for that reason, because we're after shear, this needs to be MP. Okay, and here you see the difference between 2A and 2B is just this right here. The applied shear force for case 2B is 0. It turns out the maximum reverse shear just below the base occurs when the base shear is 0. Okay, again, picking up what you would see in a time history analysis in our very simplistic approach. Okay, other than that, we've got the V at MN and the V at MP. Okay, and finally, case 3, we're interested in the best estimate of the displacements. And so nominal makes sense there, and the shear makes sense there. So as far as applied loads go, I hope that's logical, okay, and driven by the code requirements, capacity design requirements. MN, in the case of the footing design, foundation design, not for rocking, but for restrained. That's key, right? Because if you're doing a rocking footing, the requirements are different. And for shear, it's MP. Okay, and now what's left is really 3 levels of stiffness. Is it a lower bound, which means the low value, or is it an upper bound, or is it something in the middle? Okay, and that's really what this figure is talking about. So in the case of case 1, flexural stiffness in the tower wall, well, that's upper bound, okay, because we want as much as possible to go down. Stiffness of the footings, upper bound, okay? But when we are doing the other case, now suddenly when we're doing the maximum shear, these become lower bounds and lower bounds. Okay, same thing goes with the diaphragm. Okay, the diaphragm stiffness or the shear stiffness of the tower, they're lower bound, stiffness of other walls, lower bound. Okay, and then when we go to the other case, they become upper bound, upper bound, upper bound, upper bound. Okay, and finally, when we're in the estimate of displacement, we've got our best guess, which is something going to be in the middle. Now, what complicates this here, this sounds really simple, right? I mean, it sounds like a lot of work and a lot of bookkeeping, but pretty simple, right? Upper bound, lower bound, and in the middle. What complicates this further is that what's the appropriate upper bound and lower bound depends on how much force you attract. It's not something we know right off the beginning. Okay, it's not like I know in all cases what the lower bound should be or the upper bound should be. It depends how much load gets attracted. Okay, and that's what adds real complication to this, right? Is that I will guess a value and then do an analysis and find out, oops, the forces are much higher or much lower than I thought. And I can do a much better guess now that I know the force is big or small. Okay, so upper bound and lower bound is not known a priori. It's not known before. Okay, it's something you get to know better as you calculate some forces. And what I want to do is just quickly spend, I think we're doing okay for time. What I want to do is really talk about that a little bit. This is a big part of it. What are these stiffnesses? Why is there different stiffnesses for different force values? So I want to talk about that a little bit. And so what I'm going to talk about here is some recent research on effective stiffness of concrete diaphragms. And I would expect, in the commentary to the next edition of the code, we would have some refined methods, because we've been doing a lot of work on this from when the last handbook was issued. Okay, so this is work that was done by a PhD student called Marian Mahmoudi at the UBC, and she's just finishing up now. And she's done lots of nonlinear finite element analysis using a computer program developed by Professor Frank Vecchio at the University of Toronto. I would call it a state-of-the-art membrane element model. So ideal for modeling these diaphragms. And obviously, whenever you're doing research and using a nonlinear model, the first thing you have to do is calibrate your model and make sure you're predicting real numbers. So this just shows you, here's an experiment that was done on a diaphragm, okay, back in the 80s, late 70s, 80s. Not too many experiments out there. And of course, we see that we can predict that experiment very nicely. We can also predict crack patterns. So on the left is the actual test result from Nakashima, and on the right are Marian Mahmoudi's predictions using vector 2. And yeah, not exact, but pretty good predictions on the behavior of these diaphragms. So what Marion has done is studied many diaphragms of real buildings, right? So this is the core in the middle. You know, these are the foundation walls going around the outside. In the study, of course, you don't need to study the whole thing. We can just study the half, right? By putting roller supports at midspan and applying the shear in the wall here, and then using the nonlinear finite element analysis to see what's happening in the diaphragm. And Marion has spent a long time doing that. And this just shows you the kind of thing you get. So as you apply the load here in the core wall, you will start to get, the first thing you typically get are diagonal cracks. These are like deep beams, right? This is really, these diaphragms are really like thin, very deep beams. And so not surprisingly, you get diagonal cracking. And you also get flexural cracking, okay? And this is what it looks like at a shear of 5,300 kilonewtons. And this is what it looks like at a shear of 6,800 kilonewtons. Okay, quite a bit more cracking, as you would expect. Right? We got a diagonal cracks running across here, lots of flexural cracking happening here. And this cracking is what softens the diaphragm. And this is, you know, you want to reduce the shear or flexural stiffness of the diaphragm. It's all dependent on how much cracking you get, which of course depends on a variety of things. This is the kind of result you'll find. Very typical, that all of these diaphragms start out as uncracked. And so if the forces are low, you know, the uncracked stiffness is a pretty good estimate, right? So if you got really low estimates of diaphragm forces, pretty hard to justify assuming they're cracked, right? You're going to be stuck in the uncracked range, okay? On the other hand, as you crack them, of course, the stiffness decays quite rapidly as you move along. So here we're looking at load versus displacement of the diaphragm, and they look like any reinforced concrete member, you know, that has shear dominated behavior. If we actually look at how much of it is shear, so that's exactly what this curve is looking at. So the actual total load deformation is here, okay, and of that, this is the shear deformation. Okay, and the flexure is only this little tiny bit more. And that's not really a big surprise, right? These squat, and this is not a particularly squat diaphragm, right? Just to be clear, but it's not a surprise that this is really a shear element. The diaphragms are a shear element, although you still need to put in a flexural rigidity. You still need to model the flexure. And there is some flexibility coming from bending of the diaphragm. Okay, definition of stiffness. Well, like I said, this would be the stiffness in the beginning. And when you get to a load level like this is your stiffness, right? This is your effective secant stiffness. Okay, so now if we convert the load deflection curve into stiffness curve, so what is our stiffness reduction factor? Okay, how much should we reduce it? So initially it's 1, you don't reduce it at all. But once you get significant cracking, as I said before, it does drop off quite rapidly. Okay, and then it does flatten out as well. You eventually get to a flat part. So it really is, you know, these 3 different parts. And so where you are along that curve will have a huge effect on what's the right upper or lower bound. And just maybe to finish that off, this is, we've been working on refined effective stiffness models. And you can actually make an estimate of this value quite easily. And Marion has developed some simple ways of estimating the diagonal cracking shear, as well as, turns out, the flexural cracking, even though flexure is a small component of deformation, really interesting fact is flexural cracking of the diaphragms is what causes all the softening. Okay, that really surprised us in the beginning when we saw that, but that actually, even though shear deformation is key, flexural cracking is what causes the softening of the shear mechanism. Okay, and so one can do quite a refined model where you make estimates of these force levels given the dimensions of your diaphragm and the reinforcement. And then you can very easily fit curves in here for what the right effective stiffness is. Now this is if you want to do some pretty rigorous calculations and really get it exact. It turns out, look at all the data and it all fits pretty nice. So there are ways of doing that, but realize now you're talking about a non-linear effective stiffness model, and you're talking about a lot of work to iterate. The other approach, which is sort of what we're talking about, and really this is the main figure I wanted to get to before we continue, is this idea of a simple upper bound, lower bound approach. But what's your upper bound and what's your lower bound depends where you are. So for an upper bound, this is the right upper bound here. This is the right upper bound later on. And as far as lower bound goes, so if we want to do, lower bound, this is reasonable here, but this drops to here, and it's up here to start with. Okay, so this is the idea that you don't know which range you're in. Okay, and it doesn't make sense. I mean, the alternative, of course, let's just say this way. The alternative is to say, yeah, that's my extreme lower bound and that's my extreme upper bound. Yeah, it's never going to be higher than 1 and it's never going to be lower than 0.2 in this case. So you could just say, I'm going to use that, but that's pretty primitive, right? If you do that and you find yourself with a solution that's up here, then you've really done a terrible job in estimating effective stiffness. Okay, so that's the complication in all of this, is this idea that the stiffness is dependent on the force level, even the upper bound and lower bounds. Okay, so let's look at a little example problem, and we've been looking at it a few times already. This comes out of chapter 11 in the CAC handbook, and it's the chapter written by Dennis Mitchell at McGill, Patrick Pult from Sherbrooke, and myself. And I'm going to look at the example that I've done, the 11.5, which shows an example of a Vancouver building. Okay, and in that example, this is a picture of that. There is multi-floors below grade, and there is some numbers shown on how you do that calculation. Okay, and so we're actually going to look at. So this is table 1121 that looks at a summary of the forces and the stiffness assumptions used in the 4 analysis cases, okay, that we talked about. And when you actually start to do these examples, you start to see some of the complexity with these numbers and the idea that as you do the calculations, you know much more about what's the right value, and you really don't know it right to begin with. Okay, but just to see, these are the numbers I've assumed in the case 1 analysis. These were the numbers I assumed, and then I modified that, right? I modified the number and this number too, right? I assumed 1, but then before too long, I did the analysis and realized, now this wasn't a good guess, even though I'm looking for upper bound and lower bound. They're too far off, and I want to refine that before I go too much further. Okay, and then when I did case 2. Again, here, I didn't even give numbers. I said, I'm going to adjust it based on the calculated, okay? And I'm going to include the footing movements. So let's just look a little bit at the kind of results you get. So from case 1, okay, I'm after the bending moments in the tower wall, okay? And when I did it the first time, when I did case 1A, okay, where I had 1.0 ECIG, boy, that's a good upper bound, no question about that. Okay, but look at it, I'm getting these big moments in there. Okay, the moment's actually increasing below grade. And what does that tell me? That tells me I'm not going to be at 1 times ECIG. No way. If I'm getting, like, I'm having trouble, I'm gonna worried I'm not gonna have enough strength in my wall. Well, it's sure not going to be on crack. Okay, and so then I drop the stiffness down 20%, and look what happens. I go and it gets smaller. And why do I like that? Because now I don't have to worry about adding more reinforcing steel. Okay, now I've got enough capacity, and I'm going to take my reinforcing steel that I have up at the ground level, all the reinforcing steel I need here, I'm going to run it straight down, okay, all the way down to the footing. And that's not unlike sort of a typical design approach that's been used traditionally is where you don't do any analysis. You say, let me take the moment at the grade and just bring it to the footing. That's been an approach that some designers have used. And in this refined analysis, we end up with the exact same thing, okay? A lot more work, but at least we have confidence that we've done the right thing. So case one, giving me the bending moments, and the bending moments constant right down to the footing. And I'm going to design that footing. And if we just look at, this was the global analysis, right? This is what I got from the global analysis. Okay, these are my moments. And this is the solution. I've drawn it here to scale, right? This is actually drawn to scale. Okay, this is the one that I calculated by my global analysis, and this is what I've got to design for. Okay, what's the big difference? Okay, there's two big differences. One is it's not dropping off, right? This thing is going straight down. Okay, that's one. This thing's dropping off quickly, of course, and that's the main purpose of this analysis, was telling me that. The other thing, of course, is we're not here, we're way over here. Okay, and why is that? Capacity design, of course, right? What's driving this is this is in the cantilever wall direction, and as I'm sure you know, cantilever wall direction is always controlled by the steel you need in the coupled wall direction. Okay, so we've got overstrength, right? This is being driven by overstrength. Okay, overstrength. But this vertical line versus this line, that's the analysis. This is the global analysis. This is on the right is the refined analysis. Now, here are the shear forces that go with that, but these are not critical. Okay, so just for completeness, we see what's going on. But this is what's driving things like what's the right stiffness. We need to look at this. We're getting close to zero shear in the wall, okay, and getting small, very small forces in the diaphragm. And that's why we got to adjust those stiffnesses. If we go now for the second case, as I said, here I'm going to adjust the effective stiffness based on the bending moment. So, okay, what am I after now? Now I'm after what shear do I need to design the wall for? And this one I'm quite worried about, right? I want to make sure I don't underestimate that shear. And so I'm going to spend a fair bit more time to refine my analysis to get the right stiffness, okay? Because it makes a big difference, and that shear force can really change. And I'm also going to, as I mentioned before, I'm going to include flexibility of the footing, okay? Because the more flexible the footing, okay, the more goes into shear and into the diaphragm. Okay, so the very first thing is the footing rotations. Well, in clause 2110.3, okay, you can find an equation. We'll look at it in a minute, where you can actually, I'm sorry, that's commentary, my mistake, sorry. This one here. Clause 2110.3, okay, you can find an equation, okay, and that equation will give you these points. You can just calculate these points. Okay, you just put in the moment and the equation gives you these points. Okay, and then from that, you can make a very reasonable assumption that, this is sort of the linear curve in the initial range. Okay, and if you go beyond this range in here, you get nonlinear rotations. This equation in the code does give you nonlinear rotations. The other thing is, if you go to the commentary, okay, then you use more refined method, and now you're here. You get smaller displacement, smaller rotations, stiffer footing. Okay, so this guy is more work, but you get smaller rotation. Okay, and that's how it should be, right? You do the simple method, you'll get quick estimates. Okay, so that's right out of the code. This just shows you that code. We don't need to spend much time here, right? This just in 2110.332, movements of capacity protective foundations. What does that mean? It means we know the moment applied. That's what capacity protected means in this context. We know what the moment is. We can use a static analysis, okay? We have to account for the bearing stress distribution in the soil, okay, and the stiffness of the soil. Okay, and then in lieu of doing some kind of spring model, which you can always do, there's this equation. Okay, and it gives you the footing rotation in radians. Okay, when you input, the magnitude of the uniform bearing stress in the soil. Okay, and the length of the uniform bearing stress in the soil. And that's really the key here, is that if your footing is resisting the overturning with a small amount of stress out at the, high bearing stress out at the toe, it takes a lot of rotation to get there. Okay, and so, the idea that you would calculate the rotational capacity of a footing and not so much it needs to rotate to get there makes no sense. The other thing you'll find is if you make your footing a little bit bigger, the rotations come down really fast. So you can use this equation to do a performance-based design. You can add a bit of concrete, make your footing a bit bigger, and now suddenly it's much stiffer and the building gets much less drift. So again, this just shows you that idea that, if you're going to keep the bearing stresses here, well, then this thing needs to lift up, right? It needs to lift up to get that stress out on the right-hand side. Yeah, and that's the end result, but I think we've seen that. So the other thing is, like I said, that the model we use for bending in the wall or of the wall in this zone is really critical. Okay, and so we're going to use a rigorous model for the bending stiffness in this area. Okay, and how do I do that? Well, I know the reinforcement is constant, so that makes it easy. The axial load varies a little bit. Excuse me. The axial load varies through that area a little bit, but not too much. And so one can generate a moment curvature relationship, bending moment curvature relationship. And you can do that very easily, right? You throw it in program response 2000, or there's many other programs available. And what you'll get for a wall like this is a curve that's linear, and then it goes non-linear, and then eventually you reach the strength. So we know what the moment curvature response of the wall is, and of course the slope of any point in here is EI, right? That's our EI. Okay, so this would be our EI effective. Okay, a line going back through the origin representing this part of the curve. Okay, so with that, we can say that, look at, if the moment is less than 300,000 kilonewton meters, right? Well, then an EI of 1 is appropriate. And as it gets larger, that EI needs to drop. And when you're out getting close to the capacity, that EI has really dropped down, right? Because you're out here, you're at this point. Okay, so and it's worth it. I mean, this is so easy to do, and it's worth doing because you're going to get significantly different results. And this is what we see. Okay, in case 2. Okay. Remember in case 1, the bending moment went straight down, right? Now, okay, it's going over and reducing quite a bit. Okay, we don't actually care about what the bending moment is. It's just looking at it is interesting because, of course, a large gradient of bending moment means a large shear force. So here we go. This is really what we're after, is this guy, 32,100 kilonewtons. That's our shear in the level below grade. And our base shear is 18,500. So this refined analysis was really to come up with this number, 32,000 kilonewtons, because that's critical for the wall design down there. Okay, and now, again, it's always nice to go back to the global analysis and say, how does that compare? And again, you see down here, there's our global analysis, right? It was a base shear of 5,000 kilonewtons. That's the global analysis, but the capacity protected value, counting for the overstrength in bending, we have to design for a base shear of 18,500, right? So that's driving, again, that one, okay? It's driven by capacity design. So again, That's capacity design. And then finally, we get to this one, okay, which is driven by the analysis below grade. Okay, and that's really what this was all about. So instead of, you know, designing for, what was it? It was 10,000 coming out of our globe. We're actually designing for 32,000. Okay, and then finally we end up with case 3. Okay, we put the nominal bending moment on. We put a reasonable effective stiffness. We include the footing rotation. Okay, include the rotation, the spring model at the base. Okay, and we add another 0.5% drift. Okay, it's happening at the base, and we need to add that all the way up. And that's, as I said in the very beginning, that's really important for the gravity frame. Okay, any movements of the rotations of the SFRS at the bottom will help reduce the demands on the SFRS, but will increase the demands on the gravity frame. And so now the next really final discussion is, you know, is now we got to check that gravity load frame for the imposed displacements. And so with that, it comes to the end of my talk. Steve, I hope I timed it correctly.
Yes, it was perfect, Mr. Adebar. You are finished right now?
Yeah, I'm finished.
Okay. Okay, so we'll take questions. Somebody with a good question right now. Okay, I have here Kevin Pelletier. So please turn on your mics.
Hi.
Okay, you can talk.
All right, Professor Adebar, thank you for the presentation.
Welcome.
I would like to know, what do we do if we only have one story below grade? Do we have to go out through this, or do we do something else?
Yeah, if you've got one story below grade, you do not have a wall that's restrained by the structure, right? It's not going to restrain it. You're going to, effectively, you've got a footing that's going to rotate, and the main thing you need to do is account for that. The fact that you're going to get lots of movement on that footing. Yeah, that's you know, it's a completely different problem, right? But if we go right back to the very beginning, we started by saying we have a foundation that's constrained from rotating. There's a stiff, strong structure preventing it from rotating, and then we have simplified design. You have, in a sense, a completely different problem. Yeah, you still need to check the shear, but your biggest issue is going to be you're going to get a lot of movement on that footing. A lot of movement. I'll tell you, you know, out here in Vancouver, we've measured during wind. We've measured how much footings move at the bottom of 4 or 5 stories, and they move a lot. So imagine what's happening. You know, you've got 1 story below grade, and you've got an earthquake. Boy, that footing's going to move. And what does that mean? Mostly, it means damaging your gravity frame. Okay, that movement will isolate your wall. It'll protect your wall. It'll damage your gravity frame. So my answer is, the short answer is that what that just tells me is, boy, I'm really worried about the gravity frame.
All right, thank you.
Thank you.
The next question will be for Guillermo Gabrielli. So you can talk.
Hi, Perry. How are you?
Good. Good. Thank you.
Great presentation. I just going to ask you about friction, soil friction against the walls parallel to the direction of analysis. Should it be disregarded?
I think most people do, right? I think everybody pretty well. Yeah. In fact,
the other one, the follow-up is against the soil, the uncertainty of compaction, and how would you, deal with that? You have on one direction, you have soil against, being pushed against, and also the back side is being unloaded. So would you go through some sort of a more accurate analysis for the soil structure interaction? And what about actually the vertical springs?
Yeah, and those are great questions, and I don't have simple answers for you. What I will say is just about everybody I know ignores the soil and just treats it as a box sitting on a firm ground. We have had discussions out here about, well, if we're deep enough, if we really have, you know, we're 6, 7 levels below grade, why not account for that that soil? And it's helping. On the other hand, we're also having discussions around what's the right VS30 we should use to classify our soil. And everybody used to say, oh, it's definitely the VS30 below the footing. But now we're thinking, well, you know what? If you've got a big, deep foundation and there's soil beside that's, you know, fairly soft, that can push your whole structure around. And so now there's lots of discussion around maybe VS30, the site class, needs to be based on the soil from the ground if you've got a big, deep foundation. And so what I'm saying to you is those are great questions. I don't have answers. I just, yeah, I mean, we've come a long way. We used to, I mean, it wasn't that long ago on the West Coast, people would just take their tower wall at the grade and call it fixed and just ignored everything below that. And, you know, so some years ago, we started to realize, well, that's not right. And then we started to ignore all the shears down there. Said, well, we hope it cracks and it'll go away. And now we've taken 1 step, 2 steps. We've said, no, let's calculate forces down there. Let's calculate rotations. But yeah, you're bringing up some great questions, and there's still a lot to be done about refining it.
Thank you.
Thank you.
We have another question from Benoit Boulanger.
Oh, yeah.
Hi, Mr. Adebar.
Hello.
So in 21.5, anyway, you need to define your critical section for your plastic hinge. And then it really says in the code that you shall maintain the geometry in the plastic hinge. But then in the commentary, you sort of go and say, well, you need to be relatively uniform. So can you give us some guidance on?
Yeah, haven't we talked about this over a beer? I think we have, haven't we? But
probably.
So it's a great question. And are you in Toronto or Montreal? You're in Toronto, are you? Or still?
No, I'm in Montreal now.
Oh, you're back. Okay, great. So the issue is, I think in 2014 we didn't do a great job, and in 2019 we fixed it. So if you go to the 2019 CSA A23.3, that same clause, it actually says it better. It says maintain the strength, which is much better, because trying to say you got to maintain the geometry, you got to maintain the reinforcement, that actually doesn't really work very well, because you're always going to have some openings. And what does that mean? You can't have an opening? So we tried to do it, but you know, there's an expression that says the 2 things you don't want to see being made are sausages and building codes. And this is a beautiful example of that, where in 2014, I think we made some good improvements, but we didn't get it quite right. And in 2019, it's worded much better. So my answer is, yeah, look at 2019. It's done much better.
Yeah, thanks.
Thank you.
Anybody have another question? I will go with mine. Very good presentation, Mr. Adebar. It will be not a good night for me, but very good presentation. Maybe considering all phenomenon below the hinge, in the case where you have to build a new building right next to an existing one, excuse me, is it preferable to let the dilatation joint between the 2 foundation walls? In the case you're right.
So we're talking about I think you're probably talking in an area that I don't have that much expertise on. So you're talking about the exterior foundation walls, and you're right beside another building. Exactly. And the question is whether these buildings start pushing on each other, right? Is I guess effectively the issue. Exactly. So sorry, and what was your solution? I mean, how would you I mean, out here, I'm just thinking about what we do out here, and I don't think we ever do anything other than just fill it with stone. But what are the solutions? I mean, you put in some kind of styrofoam or something as an expansion joint, or
something like that. Yes.
Yeah, and neat question. And you know what? I just don't know. I haven't spent a lot of time looking at what's happening on the box on the outside. I mean, there's some, you know, it's a complex geotechnical problem when you start looking at the pressures that are coming in on the outside. And I don't think I'm the expert to advise on that. I've focused all my attention on what's happening in the tower wall as it comes down and in the soil below. But I must admit, great question. One that's too hard for me.
Okay, thanks. Anybody with another question? Maybe Rashid Idir. So maybe you don't have any mics with you. The question is, could the approach be the same in the case we have foundation on the pile? Matter of foundation rotation.
Yeah, so foundation, you've got a footing on piles. Determining the foundation rotation is obviously a more complicated problem. So now you're into talking to the geotechnical engineer for the right springs to use, soil springs to use on your piles, and modeling the pile on the axial stiffness of the pile and your friction and along the pile. So that's a more complicated problem for sure. But the good news is, from the discussion today, at least we've identified where you need to bring in that movement. I mean, you don't need to worry about footing movements for a lot of analysis, right? You don't need it in the global analysis. You don't need it in even the refined analysis when we're worried about like what the moment is coming down to the footing. It's only when we're really worried about the shears that we need to make a good estimate of what's happening down there. So what I'm saying is, the good news is you can keep the refined analysis for just the cases where it matters. And you certainly don't need to include it in the global analysis. But great question. And again, you need a geotech to advise.
Okay, thank you. We have another quick question from Brian Howard.
Professor Adebar. Just a quick question when we're looking at torsion in structures. If we want to do a static analysis below grade, do we have to consider that kind of the torsion that's applied on the structure by applying the moments in opposite directions, or are we just going purely X and Y?
That's a good question. We haven't really thought about that very much. What the torsion is going to, I don't think the torsion is going to do that much. So we've never looked at torsion, to be honest with you, and I'm quickly trying to think of where it could be a problem. So we have just like when we check the capacity design requirements for a core, even though the building might have a lot of torsion, but when we check the capacity requirements and we design the wall piers from the coupling beam strengths, and in all those steps, we don't include the effect of torsion. We take the torsion out of it, and we look at it for just bending about the principal axes. So everything we've ever thought about when it comes to designing below grade, we've always just said, yeah, ignore the torsion. But could torsion be a big, like if you had some very eccentric building, could that mean you'd need to do something different? Maybe, but I think you can just ignore it, but I want to be a bit careful there.
Okay, great. Maybe just a quick follow-up. If we want to check the torsional sensitivity of a building, should we do that with the global analysis or the refined analysis?
Yeah, the global analysis. Sure. Refined analysis just below base, just everything above base, all the forces up there, all the NBC requirements, all that, you're doing that all with just the simple model below base, and then come back to look at what's happening below ground. That's when you use the refined analysis. So yeah, keep it in the global analysis.
Great, thanks.
Thank you.
Maybe another one for Kevin Tetsier.
Hi, I have another question.
Sure.
I would like to know, I think I know the answer, but can't we just do a linear dynamic analysis with like two models, one upper bound and one lower bound, instead of going with the the other model you explained?
Yeah, you could, except how are you going to get the capacity design requirements with that? You know, because you have to meet. Yeah, but you said you knew the answer. Sorry, I'm not allowed to ask you questions, but no, I hear what you're saying. I mean, you'd like to, use your ETABS computer program or whatever computer program you use, and not have to be doing something else. But and like I said, in the U.S., they're using one model for the global and refined, and they're doing multiple time steps for that. And they have in recent, like if you look at the LA Tall Building Structural Design Council recommendation, the brand new one, they've simplified their effective stiffnesses and have less cases to do. So yeah, they're heading in that direction. But be careful, because you have to design for the capacities, right? You got to design your footing for MN if it's restrained. You still have to design it for MN. You got to determine your shears for MP. And how are you going to do all that with that model? And just scaling those linear results, does that work? Well, maybe. And then the other issue is, like I said, those effective stiffnesses are really the difficult piece. And and once you do an analysis and you know what force level you have, you probably want to adjust your stiffness. So then you're back to, are you going to do 4 or 5 ETABS runs? So anyways, I see your point. I understand the benefit of using, one ETABS model and putting it all in there. Maybe, but some things worry me about that.
All right, thank you.
Thank you.
Thank you, Mr. Adebar. I think it's okay. We don't have any question further.
Okay.
So maybe it's a thank you. It's really excited to have you with us today. So if some people want to join us in the chat, I've put a link to have a meeting with Mr. Adebar just after that. So please copy the link from the chat. It's a link with GoToMeeting. Mr. Adebar, I sent you the link in your email right at the beginning of the presentation. So just click on the link. So just a little conversation you can have. Maybe we have 10 to 15 person, maybe for 10 minutes maximum. So thank you, Mr. Adebar. Donc je vous souhaite une bonne fin de soirée tout le monde. Donc je vous invite à notre prochaine conférence.